Hi, I am Mazhar Hussain and I am presenting you a VHDL demo which is based on an FPGA device. This tutorial will introduce you how to create a rangefinder in VHDL and how to implement the design on an FPGA board. The ultrasonic sensor needs to have a trigger of minimum 10 microsecond pulse from FPGA as a command to start measuring the distance. After getting the trigger, the sensor generates sonic pulse and the response will be sent back to FPGA as pulse, whose width is proportional to the distance of the sensor from the object. In this tutorial, we are going to use Xilinx IC Design Suite, which is the synthesis, placement and simulation tool to implement the design. You can download a Xilinx IC software from Xilinx website. This tutorial is divided into these steps. Now we can start from the first step by creating a project. Launch IC Project Navigator. A screen like that will be displayed. Start a new project. In this dialog box, first choose the location of the project. We will name it to Ultrasonic Range Sensor Based Distance Measurement because we are going to implement a rangefinder on FPGA board. Leave top level source as HDL. After clicking Next, select the target device, family, which is button 3E, the package, XST as synthesis tool, ISIM as simulator, and VHDL as preferred language. Click Next and Finish. The implementation strategy to design rangefinder module on FPGA will be to define VHDL module of distance calculation, a trigger generator, a counter, a PCD converter, and a range sensor module to link all these submodules together. First part of the second step will be to define one of the module we just discussed. So let's start with the counter. Right-click near project hierarchy and select new source. Type the name of the entity of the VHDL code. Now we can specify the input-output pins of the module. The clock, enable, and reset are the inputs, and counter output will be the output. We can keep the size of the counter generic. Click Next. Ignore the warning because by default it is expecting an integer value. Click Next again and Finish. In the source pane, the set module will appear as shown. Add IEEE library packages that support keywords and operators for the VHDL language in the editor pane. In the entity of the counter, add one more line to define the size of the counter. The benefit of generic counter is that we can simply modify the size of the counter according to the need of the design at any level. After the architecture, we can write the code for counter module. Inside the process, the only difference between a normal counter and this one is that the reset is now active low, which means if reset is 0, the counter value will be 0. And the process and the architecture after giving the value of count to counter output. Save the project and select the counter module in source pane. Then in process pane, run synthesize to check the syntax. A green mark on synthesize confirms that the syntax is correct. Another module will be a distance calculation. When the FPGA will receive a pulse from range sensor, this module will convert that pulse into distance in centimeters. In the port definition, the module needs to have a clock from FPGA, a signal to reset the calculation, a pulse input, and a 9-bit signal distance to store the value. In the source pane, the set module will appear as shown. Add IEEE packages in editor pane and then instantiate a component of counter inside the architecture. There will be a need of 122-bit internal signal pulse width to record the incoming pulse duration. A port map of counter gets CLK, a pulse as enable signal, and calculation reset with a NOT gate to reset, as we know that the counter module we created have active low reset. Finally, the counter output will be linked to internal signal pulse width. Notice that the size of the counter is now 22-bit. To calculate the distance from the pulse, we need to initiate a process that should depend on input signal pulse. We can declare two variables such as result as integer and other variable multiplier as 24-bit standard logic vector to do the calculations and to temporarily store the results. The distance calculations should begin after the pulse is complete, so we can use the if statement stating that if pulse is equal to 0, then multiply the pulse width signal with 3. You might be wondering why we need to multiply it by 3. The reason is that, according to range sensor datasheet, to convert the width of the pulse into distance in centimeter, we have to measure the width in microsecond and then divide it by 58. So, for example, if x are the number of pulses in microseconds, then x by 58 is the distance in centimeter. Since the FPGA clock has a period of 20 nanoseconds because of 50 MHz frequency, which will give us a time in nanoseconds, and to convert this into centimeters, the expression should be multiplied with 20 and divided by 1000 to first get the time into microseconds. But in FPGA, the division is not simple, so instead we can use shift and subtract method. In order to solve this problem, we can multiply the expression with 3 and then shift the result to 13 position to the right, which gives us a result of 11-bit signal as shown in line 62. In the next line, we can check if the sensor reaches to its highest value, that is around 450 cm. Else, the result can be stored in 9-bit distance signal, but after further dividing it by 3, or you can say shifting 2 times to the right to get the actual distance in centimeters. Save the project and select the counter module in source pan. Then in process pan, run synthesize to check the syntax. Now the syntax is correct, so we can move to next step and create a VHDL module to generate trigger pulse for the range sensor, because the sensor will wait to get the trigger from FPGA before sending the measured distance back to the FPGA. The port definition of the module needs to have a clock from FPGA and a trigger pulse as output. Select the module in the source pan. In the editor pan, we can use the same counter we created earlier in this tutorial, but with different size, to create a trigger pulse of 100 microseconds that will be repeated continuously every after 250 milliseconds. During this 250 milliseconds, the sensor will send the measured distance. After the component of counter, as you can see that I declare 2 internal signals, reset counter and 24-bit output counter, to take the value of the counter for trigger generation. In the port map, we can hardcode the enable signal by 1 to keep it running all the time and link the internal output counter signal to counter output. In the clock process, we can generate 2 constants, one as MS250, a 24-bit signal, to generate 250 millisecond pulse. For this, we can divide the FPGA clock, which is 50 MHz, by 4 Hz. And for additional pulse of 250 millisecond plus 100 microsecond, we need to divide the clock with 3.994 Hz. This will be the second constant signal as MS250 and 100 microsecond. Now we can say if the output counter is greater than 250 millisecond value but less than 250 millisecond and 100 microsecond, then generate the trigger pulse, otherwise keep the trigger low. The counter output should be reset if the output counter is equal to the value of 250 millisecond and 100 microsecond constant. If not, then continue counting. Remember, the counter we designed earlier has an active low reset. Save the project, then select the module and run check syntax in process pan. The green mark on check syntax shows that the syntax is correct. In order to decode the measured distance, which is in binary format, we need to convert the distance into BCD, binary coded decimal format, to display the result on 7-segment displays. We can start a new VHDL module of BCD converter. In the port definition, declare a 9-bit distance input, then 4 4-bit signals that represent the hundreds, tens, and units of the measured distance. Select the module in source pan. After adding the library packages, we need to initiate a process that depends on signal distance input. Inside the process, 2 variable integer I and 21-bit standard logic vector BCD can help us converting the input distance into BCD. Before starting the conversion, we can assign the first 9 bits of BCD signal to distance input. We can use double table algorithm to convert the binary distance into useful BCD number. In the VHDL code, we can use for loop to perform this task. According to the algorithm, shift the binary number 1 bit to the left. If 8 shifts have taken place, the BCD number is in the hundreds, tens, and units column. If the binary value in any of the BCD columns is greater than 4, add 3 to the value in that BCD column. Repeat the same steps in the for loop. In the end, all the 3 BCD numbers are linked to the outputs hundreds, tens, and unit of this BCD converter module. Notice that there is an error in the transcript pan indicating a syntax error in line 36. Units is a keyword in VHDL which is not allowed to be used as signal name, so we should rename it to something else, for example unit instead of units. Now check the syntax again. This time it completed successfully. The fourth module is the range sensor module itself. This module will combine distance calculation, trigger generation, and BCD converter to a single working model. We will name it to range sensor. In the port definition, the module needs to have FPGA clock and pulse from sensor as input and trigger out as output to the sensor. Additionally, 4-bit signal that represent distance in meters, decimeters, and centimeters as output. In the source pan, the set module will appear as shown. Don't forget to add the IEEE libraries in editor pan. Under the architecture, we can instantiate component for distance calculation, trigger generator, and BCD converter. We need 2 internal signals, one 9-bit signal as distance out and another as trig out. In the port map, link the corresponding signals of trigger generator to this module, which are FPGA clock and trig out. For pulse width, map the signals of distance calculation module in the port map with range sensor module. For example, clock to FPGA clock, calculation reset to trig out, pulse to pulse, and distance to distance out. The port map of BCD converter map its distance input to distance out signal hundreds to meters, tens to decimeters, and units to centimeters. After mapping all signals, now assign the value of internal signal trig out to trigger out of the range sensor module. Now we can save the project. Notice that after saving the project, all the modules are linked to range sensor in the source pan. Now run synthesize to check the syntax. It is completed successfully with some warnings. After creating the range sensor module, the next step will be to create a module which can operate 7-segment displays mounted on a FPGA board to display the measured distance. As we already have this module ready, so we can skip this step and add the VHDL files of this existing module into the range sensor project. If we look at the strategy to combine both modules, then we can see that we need a top design that will use both segment driver and range sensor module as component and provide a connection between signals of range sensor module and segment driver. FPGA clock will be the main clock for both modules, and then all 3 4-bit signals will be mapped on disk A, disk B, disk C. We can force a constant value of 0000 to disk D, which is extra in this project. In the source pan, right click and select add source. Go to the 7-segment display folder and choose all the submodules required to complete the segment driver. Choose the files of clock divider, segment decoder, and segment driver with .vhd extension. In the source pan, we can see that the segment driver is now visible together with submodules of counter and clock divider and segment decoder. As I said earlier, the top design will link both modules to work as complete system, so let's define it. In the port definition, we can declare pulse pin as input, trigger pin as output, clock as input clock, the selection signal for display B, display C, and display D as output, and finally the elements of 7-segment displays as output. In the top design module, now add the standard IEEE library packages in the editor pan. Then instantiate range sensor component and segment driver component. Add 4-bit internal signals AI, BI, CI, and DI. Add another 4-bit internal signals sensor meter, sensor decimeter, and sensor centimeters. In the port map, assign the display A, B, C, and D to internal signals AI, BI, CI, and DI, and rest of the segments and selections to corresponding top design signals listed in the entity. In the port map of range sensor, assign CLK to FPGA CLK, trigger out to trigger pin, pulse to pulse pin, and meters, decimeters, and centimeters to internal signals, sensor meter, sensor decimeters, and sensor centimeters. Finally, assign these three signals to AI, BI, and CI respectively. Hardcode the value 0000 in DI because there is no need of 4th display in this project. Now save the project. Notice in transcript pane that there is an error in line 60 near component. The error is because we forgot to end the range sensor component. By adding the missing command will solve the issue. Now if we save the project, all the modules will be linked to top design in source pane. To check the syntax, run synthesize in process pane. The synthesize completed successfully with some warnings. Now we are moving towards final steps. Among them is a configuration of constraint file. Download master UCF file for Nexus 2 1200 FPGA board from Digilent website and add it in the project folder. Unzip the file in the project folder. Right-click in the source pane and select Add Source to add UCF file into the project. Click on UCF file and in process pane choose Edit Constraints. Replace the constraint for clock with CLK of top design entity list. Similarly, replace all the elements of 7-segment display and segment display selections. To connect sensor to the FPGA board, we need two I/O pins. For example, we can choose JC4 for pulse pin and JC5 for trigger pin. To avoid error during place and route process, we need to include this line to show that the pulse pin is not a clock pin. Save the project and proceed to generate bit programming file, which will be used to implement the final design on FPGA board. Select the top design in source pane and then click on Implement Design in process pane. As you can see, the process completed successfully. Now run the generate programming file in the process pane. The green mark shows that the bit file is ready to download in FPGA board. As you can see that I have USB mini cable, FPGA board with 7-segment displays and a range sensor to make it a complete range finder. We can set up the FPGA board by connecting it with range sensor and to the computer using a USB cable. Open Digilent Adapt, which is a programming software to download the bit file into FPGA board. Select the top design.bit file from the range sensor project folder and click on Program. Now the setup is ready to measure the distance and to display it on the 7-segment displays. The 4 wires that are connecting range sensor to FPGA are 5-volt power supply, a ground, a trigger for range sensor, and a pulse from range sensor. You can see that when I move my hand in front of the sensor, the distance value changes on segment displays. The update rate is not so fast because we are using longer trigger period. One can give fast triggers by modifying the trigger module to increase the update rate. This project verifies the VHDL code that we implemented during this tutorial for ultrasonic range sensor to measure the distance using an FPGA.